of functional groups. So this is the end of our organic chemistry unit. Next up will be the biochem unit. The unit 17, 18, and 19 will still feel a little bit like organic chemistry, but we'll be moving into what we call macromolecules. So this is our last video on functional groups. And this concludes Unit 3. Today we'll be talking about amines and amides. So again, just like we've done with all our other functional groups, we'll be talking about the structure, how to name them, discuss physical properties of these functional groups, as well as important reactions with them. We'll also talk a little bit about some common names for these, as well as some important ones that we see in biology. So the first thing we need to talk about so far with amines are that they are derivatives of ammonia, so the compound NH3. And just like we had with our alcohols, where we had primary, secondary, and tertiary alcohols, we can have primary, secondary, and tertiary amines. And so what we're looking at here is how many different R groups are around that nitrogen. So a primary amine has one R group or two hydrogens. A secondary amine has two R groups or one hydrogen. And a tertiary amine has three R groups or no hydrogens around it. So it would look something like this. So go ahead and identify the type of amine this compound is. Go ahead and do the same with this one. So instead of having the words primary, secondary, tertiary, quaternary, we use 1 with a degree symbol to represent primary, 2 with a degree symbol to represent secondary, 3 tertiary, quaternary would be 4. So this is a tertiary amine. Oop. So we do have some common names that we'll see in our amines, as well as going through the IUPAC naming system. This is the common names are typically for our very, very small amines. And what we end up seeing is things as simple as describing something as methylamine or dimethylamine. In this case here, we have ethyl-methylamine. And essentially what it's doing is going through the different R groups and naming them, and we would name them in alphabetical order. So ethyl comes before methyl, and so on and so forth. When we're doing our IUPAC naming system, we're going to go back to the same rules that we've been using up until this point, which include finding the longest chain of carbons that contains the nitrogen group on it. And just like we have been doing, so if you had propane or butane, it would become, we'd cut off the E and add amine, so it would be butamine or propamine. We also use the number of the different carbon chain to identify where the substituents are, as well as a capital N, and it's written in italics if there's going to be anything attached to the nitrogen. So we'll talk about that when we look at this one here. So the first one we have here is we have 1, 2, 3, 4, 5 carbons, so that's some sort of pentamine. And we know that we have it on the 2 carbons, so this would be 2-pentanamine. Here we have our nitrogen, and it's on 1, 2, 3, 4 carbons. We could also go 1, 2, 3, 4 carbons this way. So either way we have a butanamine. And the 1 here is representing the nitrogen is on the 1 carbon. And then we're saying that on the 1, 2, 3 carbon, there's a methyl group. So 3-methyl, 1-butanamine. And then lastly here, our longest carbon chain, 1, 2, 3, 4 carbons long. So we have a butanamine, and the nitrogen is on the 2 carbons, so 2-butanamine. But we haven't represented this methyl group here, and the way we do that is by saying N-methyl. So it's literally just calling out that on the nitrogen branch of the chain, there's a methyl group. We can also have this on aromatic compounds. We've already seen the simplest of them where we have an amino group on a benzene ring, and this is called aniline. Anytime we need to do anything more complicated than that, we're going to use the same rules that we've been using. Again, in this case, we have N-methyl, or excuse me, 2-ethyl. Again, our aniline is the number 1, so 1, 2-ethyl, N-methyl aniline. And the methyl, N-methyl, comes from this methyl group being attached to the N and not to the rest of the chain. So go ahead and answer the following compound. This would be N-methylphenol. You could also, or excuse me, oops, that's an error. This should be N-methylaniline. So it is not N-methylphenol. This is not a methyl group. Sorry about that, folks. This is N-methylaniline. We have our aniline. Here's our benzene ring with our NH group, and we have a methyl group off to the side. So N-methylaniline is the correct answer. Which of the following is not appropriate name for the following compound? Here we have 1-methyl-2-aminotoluene. So in this case, the reason toluene doesn't make any sense is we're saying 1-methyl-2-aminotoluene. We would be saying that the nitrogen group would be the secondary group instead of having it be one of our aniline groups. Go ahead and name this compound. So again, we have a salt now, so we're going to have our iodide and our N-ethylaluminium iodide. Again, it's very important that you're reading in your textbook as well, the assigned reading. There is a lot more detail than we have time to be able to go through. Please read, take notes, and come to office hours. It's the best way to learn this material. So we need to talk about some of the physical properties of our amines. Again, smaller, low molecular weight amines will be gases at room temperature, but the bigger, more complex ones tend to be liquids, sometimes even solids. An NH bond is not quite as polar as an OH bond, but we will still see polarity with that. So that's how we're getting some liquids and solids out of this. Primary and secondary amines form hydrogen bonding with each other, which makes sense because they have hydrogens available to them still. Tertiary amines can never form hydrogen bonds because there's no hydrogen bound to a nitrogen to be able to do that. Because the NH bond is slightly less polar than the OH bond, their boiling points will be a little smaller and lower than those of alcohols. So here's an example going through and showing you the different hydrogen bondings that can occur when we have water present. So this will affect solubilities of our compounds in water. We also can talk about things like their odor. So we knew with our carboxylic acids we had a sharp odor, similar to that of ammonia. If you've ever had an ammonia-based cleaning product before, or an ammonia-based like hair dye, the very like pungent smell you get with that. Amines are also responsible for kind of the smell of like rotting and decaying flesh. So there are compounds called putrescine, which is a very putrid smell, and cadaverine, which as the name suggests is kind of similar to some of the smells associated with, rotting corpses. So again, looking at the structure of these different amines, we can relate that to their melting and boiling points. And again, we can see the bigger they get on the whole, the higher the melting point becomes, the higher the boiling point becomes. Again, be able to relate these boiling points to their inter-ER molecular forces that are occurring. So in the amine that we have presented here, what is the strongest intermolecular force, right? We would say that primary alcohols are going to have the strongest because we know an OH bond is going to be slightly more polar than an NH bond. So primary amines versus primary alcohols. The alcohols will have stronger intermolecular forces. Ethers are not really polar, and thiols are even less so than the amines. So we have some general reactions that occur with amines, just like we've had with all our other chemistry. A lot of this will be acid-base chemistry because amines are considered weak bases. So they produce hydroxide in water. So here we have methylamine in water, and we produce a cation and an anion, right? We're back to acid-base chemistry here. So the trick is always here. This is a weak base, which means the the water would be acting as the acid. So we're going to end up with a salt. Just like we saw with our carboxylate ions, we're going to get an amine salt as well. And so when we're naming these, this would be methylammonium chloride, and it comes from methylamine. So we cut off the amine portion and add ammonium and the name of whatever anion comes with it. Amines react with acids to form salts, so we could have a number of different acids present. In fact, we could even have a carboxylic acid present, which would give us this very, very complex compound here. Well, we have ethyl ammonium, which is this portion here, acetate. So amine salts, when we name them, we just change the amine portion of the name to ammonium, and then we add whatever anion is present with it. So whether it's a bromine, a chlorine, an acetate, whatever it may be. Amines can be converted back into, the ammonium salt can be converted back into an amine with a strong base. So if an acid is what makes the ammonium salt, a base will make our amine again. So again, this is pH driven, so if you need to go back and review some of our pH acid-base chemistry, I would encourage you to do so, but remembering things like solutions that have low pH, which are going to be acidic, will form salts of the amines, and when we have solutions that are high pH or very basic, we're going to get the amine back out. We will talk a little bit more about quaternary salts when we get to our biological section again. I just wanted to bring this up for you. So we talked about primary, secondary, and tertiary amines. This would technically be a quaternary amine, but this needs to be, this will be a cation. Go through and do your Lewis structure, determine why and where this positive charge comes for this whole molecule. So it needs to be balanced out by an anion. So these are always going to be salts. These quaternary salts are really important in things like medicines and different disinfectants, and oftentimes what ends up happening is we know that ionic compounds are very soluble in water, so making these quaternary ammonium salts is one way to help these compounds and medicines and those kinds of things be more soluble in our bodies. Our bodies are primarily made up of water, so if we can have something that is water soluble, it's going to be more effective and get to the areas that it needs to get to. So when we mix an amine with HCl, which is an acid, what will we produce? Amine, weak base, plus an acid will give us the ammonium salt. The other functional group that we're going to talk about is an amide. So we have amines and we have amides. Amides are the nitrogen equivalent of an ester. So an ester, there would be an oxygen here, right? And an ester was the sandwiched oxygen where one of the carbons had to be a carbonyl. An amide is going to be the nitrogen version of that. So to form an amide, we're going to have a carboxylic acid and some sort of amine or ammonia. And just like with an ester where you could determine the reactants, right, the mom and dad, the parents that made the ester, you can determine the parents that make an amide. So you can do this with acid chlorides and anhydrides the same way we did them when we were looking at ester formation. So it's always going to be some sort of carboxylic acid or acid chloride or acid anhydride plus an amine to form an amide. Now, this is a primary amine here, but we won't be able to do this with tertiary amines because we need a nitrogen present to make this happen. So if we have a tertiary amine with an acid chloride or the anhydride, we won't have a reaction produce an amide. There won't be any reaction going. So again, here we show our little map that takes us through the different types of amines that we can make, or the different reactions an amine can undergo. Again, just like we saw with our esters, where we could have polyesters, we can have polyamides in the same way. Just like we had our polyesters, we can have a polyamide. This will be really important when we get to our biological section and we're talking about things with proteins and amino acids. They're also really important in things like our industrial materials, so things like nylon and fasteners, and basically a lot of like nylon materials are made from polyamides. So we do use a lot of it. So here, when a diacid reacts with a diamine, which of the following is produced? So something like this, we're going to produce a polyamide. The other really important biological aspect of these nitrogen-containing compounds is their importance in our bodies. They are really a part of our nervous system. So nitrogens are part of our neurotransmitter system within our bodies. And so again, we'll be talking primarily about these nitrogen-containing compounds when we get to our biological section. But ones that we see a lot would be things like serotonin, dopamine, acetylcholine. These are all those amide and amine type structures that are crucial to parts of our body. So we can see things like serotonin, which has a primary amine over here, and it has a cyclical and cyclical secondary amine right here. We can also have other types of important biological amines that are also a part of kind of our central nervous system, part of a lot of our brain chemistry, how we feel about a lot of things. And these are whether or not they are uptaken into our brains and downtaken and that kind of thing. So we will learn more about these when we get to our biological section, but tyrosine is an amino acid. And then dopa and dopamine are other amino groups that kind of go through this process, right, where we take tyrosine and it becomes dopa, then it becomes dopamine, and we end up using it as we uptake it into our bodies. Serotonin is another very important biological compound that comes from an amino type compound. Functional groups, and again, a lot of these compounds are going to be associated with our brain chemistry. Other ones will be part of like our hormone responses. So epinephrine is a part of our flight or fight response. So when you have like a panic attack and things like that, or you're put in a situation that is high stress, our bodies release these hormones, or not, they're not hormones, but these compounds. Amphetamines, these can also be very powerful stimulants. If you look at the structure of epinephrine versus amphetamine, you can see that physically the Lewis structure is very, very similar, which is important to how it's able to react in our body. Obviously, amphetamines also have a negative association with them as well. So, for example, things like methamphetamines or meth obviously are highly addictive, can have negative effects when abused as a recreational drug. The other type of important amines that we'll see in our biological sections are things called alkaloids. So these are typically nitrogen-containing compounds that are found in plants. So everything from nicotine to caffeine to THC to things found in peyote, basically every psychotropic drug that is plant-based it has some sort of alkaloid in it, which is a nitrogen-containing organic compound. So one that I'm sure we're all using and abusing right now might be caffeine, which looks something like this. And again is really, really a stimulant, a mild stimulant. Obviously, some people are more sensitive to it than others. It is very, very soluble, so much so that it can cross the placenta barrier, and therefore you can reach a fetus. A pregnant woman can caffeinate their fetus. Sometimes we have alkaloids, these plant-based nitrogen-containing compounds that are for medicinal use as well. So quinine, which is part of a malaria treatment, quinine is found in, probably the most common thing it's found in would be tonic water. So if you are drinking tonic water that has quinine in it, there's kind of a tangy taste to it that you might be familiar with. Obviously, other alkaloids that we know of are things like opium, which is what we derive morphine and codeine from, which are parts of pain relievers. Obviously, you can see the similarity between morphine, codeine, and then the drug heroin, which are all based off of the same opioid. And obviously, we know heroin is highly addictive and is easily abused. So go ahead, try and answer this question to the best of your ability. So we know that the salts, remember, a salt is always going to be more soluble simply because now we have an ionic compound. And ionic compounds go back to our understanding that secret language of I know that you know, that, you know, when we see an ionic compound in aqueous solution, that really means that it's the separated two ions. So we have talked about how we name amines. We're going to talk a little bit about how we would name an amide. So just like with esters, where we knew that the ester was formed from the carboxylic acid and the alcohol, we do the same thing with amides. There's some carboxylic acid and there's some amine or ammonia present, and each of those are put together to give us the name. If we have a more complex amide, there are a couple different ways you could name it. So you could, in the examples we have here, where we use the N formation of it. So we have N-methylformamide, or we could say it as, this would be the common name. The IUPAC name would be N-methylmethanamide. So N-methyl, coming from this portion right here, N-methyl, and then this was from the carboxylic acid, would be the methanoic acid, so methanamide. Again, up here we have the acetic acid, or we could say the diethyl acetate, and our N,N-dimethylamine that were brought two together to make N,N-dimethylacetamide, or you could say N,N-dimethylethanamide. Again, I am aware that these are very, very complex. This is something that comes with practice. This is not something that you can just memorize. There are thousands of millions of different combinations that could exist for these compounds. So it's really about learning the rules and then just applying those rules. So go ahead and answer the following question for this one. Here's a good example of an amide. This is a secondary amine. This is not anything. This is just some sort of organic compound. And this is a carboxylic acid. What is the IUPAC name of the following compound? This would be N-ethylpropanamide. So we have an amide, and then we need to go through and determine this was the carboxylic acid, this was the amine that came together. Here's our amide bond. So just like we've done with all our other functional groups, we can go through and discuss some of the physical properties of amides. So amides have the ability to hydrogen bond with themselves as well as with water. So, but we have to keep in mind whether it was a primary, secondary amide that we formed. Obviously, the more hydrogen we have, the more hydrogen bonding that can occur. Because of this complex hydrogen bonding, we have very high melting points for these. So here again, we're just showing the water solubility of these compounds, right? Because an unsubstituted amide, right, where we have a lot of hydrogen present, can make a lot of hydrogen bonds with water, therefore would be very, very soluble. And then when we start getting some substitution going on, where those hydrogens are replaced by R groups, we still have some hydrogen bonding going on with water, but not nearly as much as we did with the unsubstituted. So go ahead and try and answer this question. So the one reaction that we're really going to focus on with amides would be how to break them apart. So we know that a carboxylic acid and an amine make an amide, so the hydrolysis of an amide would produce the carboxylic acid and an amine again. Now, if we do this under acidic conditions, we would get the carboxylic acid. If we do it under basic conditions, we can't get an acid in base, so we would end up with the salt. So we'll see what that looks like. So here's an amide plus water and acid, which means we would get the carboxylic acid and the amine salt out. Here we have another example of the carboxylic acid and the amine salt. Here's an example where we have the amide and a base. So we cannot get the carboxylic acid out because we're in base. So we're going to get the salt and the amine. Because the amine is basic, that's how we get the amine out and not the amine salts. We need strong acid or base to do this, so again, this would just be one of those things that I think makes a really good flashcard to kind of go through and learn the rules of what is produced when we're under acidic conditions versus what is produced when we're under acid conditions. As we talked about, these amines and amides are really, really important in terms of medicinal chemistry and medicines that are made. So things like ampicillin or thiopentanol, which are used for asthma, tranquilizers, antibiotics. It's a wide variety of different medicinal compounds that utilize amines and amides. So under basic hydrolysis, so under base conditions, when we hydrolyze amides, we produce what? We'll produce a carboxylate salt, so not the carboxylic acid, we produce the salt of the carboxylic acid and the amine. And that is the end of Chapter 16. This concludes Unit 3 and the materials of the different functional groups. You will need to be able to relate things like inter-ER molecular forces to boiling points in comparing different functional groups. You will have to be able to do different reactions, multi-step reactions, take a compound and name it, take the name of a compound and draw it. Please make sure you're looking at your homework and your extra help. I really encourage you to do the reading in the text and to come to office hours.